Hello, in this lesson we'll be talking about the product rule for derivatives. So the goal is the following, is to say that we have some function h of x made up of f of x times g of x. Our goal is to find what is the derivative of this. So in other words, h prime of x is equal to something, and our goal is to discover this. So what I'm going to do is pose an example that we know the answer to, give you, rather than just give you the proof to start, give you a bit of more of an inductive argument for it, and then we'll go and actually formally prove this derivative. So the first thing is, let me start with a potential f of x as 2x and a g of x as 3x to the fifth. Okay, so first of all, we know that f of x times g of x is equal to 6x to the sixth, and we know the derivative of this will equal 36x to the fifth. This is something we know to be true. But I'm going to make the claim here that what we can do is actually, and this will sound a little strange, but listen slowly, I should say, we're going to do the derivative of the first function times the second function plus the derivative of the second function times the first function. So, in other words, if, in this case, we'll do f of x times g prime of x plus f prime of x times g of x. So this function times the derivative of the second one, this function's derivative times the function itself, the second function. So now if we take 2x, derivative of g is 15x to the fourth. This one's the derivative of the first one, and that's 2. And then g itself is 3x to the fifth. So we get 30x to the fifth plus 6x to the fifth, which is 36x to the fifth. And we knew ahead of time that the derivative should have been 36x to the fifth because we actually were able to multiply f and g together. Now, obviously, this rule is developed for functions that are not so easy to just lump together, such as these where you just add the exponents. For example, if you're given a function like x to the fifth and sine of x, now you've got to deal with two different functions that you can't easily write as one function. So again, h, back over to our abstract side, h is defined as the multiple of f and g, and we're looking for h prime. So the first thing is that we'll use our good old limit definition, which is the limit as h approaches 0 of h of x plus, and I'm realizing now that maybe my choice of h wasn't so great. I'm just going to rename my function h. Sorry for that. Let's say it's j of x, and this will be j prime. So now my function will be j of x plus h minus j of x over h. And hopefully you understand why I chose to rename that. So the thing is, j of x plus h is x plus h plugged into both of these. And that would be f of x plus h, g of x plus h, minus f of x, g of x. Okay, and our goal is, of course, to figure out an expression for this. I've already shown you via an example that this is the case. It turns out to be the first function times the derivative of the second function plus the derivative of the first times the second. And of course, all these operations commute, so it might show up a little bit differently here, but it'll show up as the same, as an equal expression to that. So I'm just going to get rid of this. Again, the reason I made this argument over here was it was a function that we could easily combine and check with. And I thought if I put the abstract proof up here, it might be a little strange to you upon first sight if you didn't have some sort of example to go by, especially with all these different function names. So what we're going to do now is make a sort of interesting choice here. But you can see that there's not exactly anything we can factor. The h's can't exactly cancel away. So we've got to make some kind of move here. And what we're going to do is we're going to add and subtract a value. So something here and here, we're going to add this thing and then subtract this thing. And they will result in 0, or maybe it's a subtract and add. It depends on how you want to look at it. But the point is, whatever we put here and here must be the same so that they are 0, thus preserving the equality between this expression and our next expression. So maybe pause it a second and think what would be an advantageous multiple, or an advantageous term to put here and here. Okay, so I'm actually going to do a subtract and an add, and we're going to do minus f of x plus h, g of x, plus f of x plus h, g of x. So again, one thing I'd like you to see here is just looking at these two terms. If I kind of box them out, these two terms are 0. So I haven't actually impacted the expression that we're working with, just have rewritten it in what we'll see is a more user-friendly way. Now, if you see here, we've got two separate groupings that we can deal with. This grouping, the first two terms, and then the last two terms. Okay? So I'm just going to get rid of this red line here. So think about how we can find an expression that has anything to do with a derivative. Oops, sorry, just realized I left off that last g of x. So remember, derivatives look like this. So we're going to take our first two terms in the numerator, and we're going to factor an f of x plus h out of it. I'm going to put it in a different color just so that it stands out a little bit for you. You see how f of x plus h goes into both of these terms? So then we're left with g of x plus h minus g of x. Hopefully at that point, little messages going off in your head like, oh yeah, that looks like a derivative. That's a good thing. And then we're also going to factor out of this one a g of x. And I told you that I was going to color code them, so I will. And this will be f of x plus h minus f of x. And all that goes over h. Okay, I'm going to resume my work up here. Now you can see that this thing, well, if we separate it, let's first separate our two things. We've got plus here, so I'm going to do limit as h approaches 0 of f of x plus h, g of x plus h minus g of x over h plus g of x, f of x plus h minus f of x over h. Now, if you now let h go to 0, this term right here, that green guy right there, when h goes to 0, that just becomes f of x. When h goes to 0 of this expression, g of x plus h minus g of x over h, that is defined as g prime of x. And here we start seeing the formation of our general rule. And then we take our next function, g of x is already g of x. But we're left on the right here, when h goes to 0, this whole thing that I'm blocking out, you can see just that, that's defined as f prime of x. And there we have it, the derivative of a product of two functions f and g is equal to first function times derivative of second plus second function times derivative of first. We'll do one quick example with this and then move on to something else. Okay, so this example will be x e to the x. Let's say the function is equal to x e to the x. You can see our product here is the function x times the function e to the x. So f prime will be first thing times derivative of second. And remember the special fact about e, we defined it in such a way that it was its own derivative, plus second thing times the derivative of the first. And the derivative of x is simply 1. So this derivative is equal to x e to the x plus e to the x. Now just for, just out of interest with this function, I'm now going to take the second derivative, and you notice the notation f double prime. There's a product rule to deal with here, but not there. So first, the derivative is x e to the x plus e to the x times 1. That was just the derivative of this term, x e to the x, e to the x times 1, plus another e to the x. And you can see what's a little bit interesting about this function to me is that each time, so that's actually equal to x e to the x plus 2e to the x. And you can see that every subsequent derivative we take, we'll get more and more e to the x terms on the side. And that's, such is the nature of e. It has all kinds of weird functions like this. So this is just one example of how to use a product rule, but the major theme is derivative, or in whatever order, first function times derivative of second, plus second function times derivative of first. We will be covering the quotient rules in subsequent lessons.